Okay, our next topic is Taylor theorems. Okay, Taylor theorems. Taylor theorem is an approach to the problem of functions. Approximation is to construct a polynomial that, together with the derivative, and takes some same values as those of function and derive at it particular. Means that it's an approach for you to calculate the approximation function. So in terms of Taylor theorems, it's based on polynomial px. For example, p a f function a, p prime a, or f prime a, and p double prime a, and the rest. Okay. Okay, for example, we go for the example. Find polynomial approximation of the function of fx such f node fx0 equal to 3, f prime 0 equal to 4, and f double prime 0 equal to negative 10, and f triple prime is equal to 12. So here is, by using Taylor's theorems, you need to find the main functions. So how we want to do it is, in this case, we know that the first three derivative x equal to 0. So means that we can create our function of px equals to a as a constant, b bx plus cx squared plus dx power of 3. So then we go for each of conditions. The first condition said that when x is 0, the answer is 3. So we put it x0 and put x0. This one will cancel, this one will cancel. So automatically your a value is 3. Okay. So second, f primes is equal to 0 is equal to 4. So you differentiate this one in terms of first differentiation. You get b plus 2cx plus 3 dx squared. So when you put it, x is 0, so your answer is 4. So automatically we know that this one will cancel, this one will cancels. Then your b is 4. Okay. So then x double prime, you will get 2c plus 6 dx. So when you put it, your x value is 0. So your answer is negative 10. So when you put it at x is 0, this one cancels. So automatically you'll see you get negative 5. And you have a x triple prime is 6d. So when x is 0, automatically you will get the answer is 12. And your d is 2. So when you put everything in your equations, so this is your final equation, which is your a is 3 plus 4, b is 4, 4x minus 5x squared and 2x power of 3. So this is your final polynomial of equations. Okay. So for example, we go for examples 9.9. So the same equations but different condition. Where is your fx when x is 1 is equal to 1, and f prime 1 is equal to 0, f double prime 1 equal to 2, and f triple 1 equal to 12. In this case, we know that automatically is when x equal to 1, okay, the answer is 4. So from here, we know the functions. When we create the functions, is automatically we know that we get a px is equal to a for first operatory, then b, then x minus 1, because of when x is equal to 1, 1 minus 1 becomes 0, everything becomes 0. So automatically you get the a value. So you will get this bx minus 1, cx minus 1 square, and dx minus 1 power of 3. So when x equal to 1s, okay, so automatically this one will become 0. This one will be cancelled 0 and 0. So automatically you get your a is 4. So f prime 1, you differentiate this one in first differentiation. Then you put it your x equal to 1, you will get b equal to 0. So you differentiate 2 times, okay? Then you put it your x equal to 1, you get 2. And differentiate 3 times, you will get your d is 12. So then you put everything inside the main function. So what is your a? A is 4. Plus what is your b? B is 0. Okay, 0, x minus 1. What is your c? C is 1. Okay, c is 1. So c equal to 2 divided by 2 equal to 1. So you get x minus 1 square plus what is your d? D is 2x minus 1 power of 3. So automatically your final function will be something like this. 4 plus x minus 1 square plus 2x minus 1 power of 3. So such polynomial approximation to function are called polynomial Taylor's polynomial. We call it as a Taylor's polynomial. So in general, the Taylor polynomial can be represented something like this, where it is your Pn, the first function fa plus x minus a divided by 1 factorial f prime a, and x minus 2 power of 2, so divided by 2 factorial of f double prime a, x minus a 3 power of 3 divided by 3 factorial f third differentiation, and the rest. So we know that clearly that f, p, and a equal to fn. So the first derivation of fn can match the derivation of x, fx is equal to x equal to a. Then the approximation of x is given the line of which is your fx is equal to pn plus rn, whereas your rn we call it as a remainder. And the remainder term can be expressed in many differentiation with simplest knowing of Lagrange form. Okay. So which is Rn equal to this Lagrange form. So in terms of theorem of Taylor's theorem, we can simplify something like this, which is fx equal to the first function fx a x minus a divided by 1 factorial f prime x and the rest. Okay, from equation 9.10. Okay, for the Taylor's and Maclaurin series, an alternative form of Taylor's polynomial of 9.10, okay, which obtain when we replace x is the expansion of a plus x, then we obtain a polynomial of x rather than x minus a. So we can simplify, become x plus a become fx x divided by 1 factorial f prime a x2 2 factorial f prime a and the rest plus and rn. Whereas your Rn is x n minus n plus 1 divided by n plus 1 factorial of fn plus 1 and a plus theta x, whereas your theta should be in the range of 1 and 0. So this equation of 9, we can call it as a Taylor polynomial expansion of fx about x equal to a. Okay, so in terms of remainder Rn, it can be represented by the error involved of fx by the polynomial, which is fa equal to x 1 factorial f prime a and the rest, whereas your Rn is equal to 0 when n is infinity. So the equation of power series is fx plus a is equal to fa x 1 factorial f prime a x cos power of 2 2 factorial and the rest lah. This is the general equations. So this one we call it as a Taylor series expansion of fx about x equal to a. Okay. Similarly, Rn, the remainder may tend to be 0 as n is infinity. Okay. So the restriction interval value of x and not at all. In the case of the power series of 9.12 will only represent the fx function of the conversion. So this one is a setting of 9.3 when a f0. So we call it as a Maclaurin series expansion of x. Okay, we go for examples. Finds Maclaurin series expansion of exponent x sine x. So we know that sine for the function fx exponent x sine x, when we derive for the first derivation, we get exponent x sine x plus cos x. Okay, so this one when we can by using the identity, you can get this one square root of 2 exponent x sine x plus 1 over 4 pi. So from here, when we differentiate this the second time, we will get something like this, or square root of 2 power of 2 exponent x sine x plus 2 plus 1 times 1 over 4 pi, or equal to 2 exponent x cos x. So on. this can be simplified to be f power of k, any differentiation is x equal to square root of 2 power of k exponent x sine x plus 1 over 4 k pi. So when we put x equal to 0 for the fx function, the first function, this one, so we will get equal to 0. Okay, when the first derivative function, this one, the second one, when you put x equal to 0, you get 1. Then second derivative, when x equal to 0, you get 2. Okay, when third derivative, when x equal to 0, you get 2. And fourth derivative, when x equal to 0, equals 0. And also the fifth derivative equal to -4, and sixth derivative equal to -8. So when we substitute everything in these functions, so we get the first one is become 0 plus x times the function of first derivative is 1 plus 1 over 2 factorial x squared times the function is become 2 plus 1 factorial 3 x squared over 3 power of times 2 and 1 over 4 factorial x power of 4, what is the answer is 0, then 1 over 5 factorial x power of -4, and the rest at the end you get the general equation of x plus x squared plus 1 over 3 x squared over 3 minus 1 over 3 x power n, and the rest. So this is on how to find the expansion series of Maclaurin series using the function of exponent x sine x. Okay, so it remains to show that Rn remainder is approximate to 0 when n is infinity. So from here, we have a particular examples of Rn, where is xn power of n plus 1 factorial of this function as square root of 2 n plus 1 exponent theta. So this one, then we recall the series of conversions. Then we calculate the Maclaurin expansion. At the end, you get exponent x sine x equal to x plus x power of 3, 2 plus 1 over 3 x power 3 minus 1 over 30 x power of 5, and the rest. So this is the Maclaurin expansion in order by using the Taylor's and Maclaurin series. Okay, here is the summarization of Taylor and Maclaurin series. Okay, for the first one, if you get the function is 1 plus x power of r, so you can use this Maclaurin series of the first one. Then if exponent 1, you can use the Maclaurin series of this one. If sine x, you can use this one. Cos x, you can use this one, and the rest. Okay. So for example 9.11, using Maclaurin series expansion of exponent x and sine x, confirm Maclaurin series expansion x obtained in 9.10. Okay, just now the function is the same, exponent x sine x, but the Maclaurin series using the derivation of method. But here we use based on the series of theorem. So now we have two function here, which is exponent x, the second function sine x. So what is exponent x? You can refer to the table here. Exponent x, you can use this one, and sine x, you can use this one. Okay, so exponent x is 1 plus x divided 1 factorial plus x squared divided by 2 factorial and x3 power of 3 divided by 3 factorial and the rest. Meanwhile, for sine x, you can use the formula of x minus x power of 3 factorial plus x power of 5 factorial and the rest. So this is for individual exponent and also sine x. So here you can multiply both of it in order for you to get exponent x sine x. You can use this series in order, then multiply. For the first series exponent is something like this, and the second exponent is sine, something like this. So when you multiply, you can get the final answer is x plus x squared plus 1 over 3x power of 3 minus 1 of 30x power 5 and the rest. So you can notice this is answer is the same answer by using the Maclaurin series of differentiation. Okay, the same one like this. Okay, so the Maclaurin series have simplified using this series. So you just plug and play the answer. So we go for next example, 9.12. Obtain the binomial expansion of 1 minus x squared power of negative 1 over 2 and deduce the power series for the sine inverse. Okay, so the main power series is 1. We can use this series 1 plus x power of r. So this is the series. So back again. Okay, continue. Okay, so based on these functions, so we will compare with 1 plus xr. So we can compare here. So we know our r is become negative 1 over 2, and we replace x with negative x squared. So we put it 1 plus x first. When the r is negative 1 over r, so 1 plus r. What is r? R is negative 1 over 2 divided by 1 times x. Okay, we put it the main function first, which is we solve it the r first. We put it the r first. Okay, plus r. What is r? Is negative 1 over 2. So negative 1 over 2 minus 1 become negative 3 over 2 divided by 1 times 2 factorial. So x squared. Then we do the r. What is r? Is negative 1 over 2. R minus 1 become negative 3 over 2. R minus 2 become negative 3 over 2 divided by 1 times 2 times 3, or 3 factorial, x power of 3. And in terms of 4 also, what is r? R is negative 1 over 2. R minus 1 is negative 3 over 2. R minus 2 become negative 5 over 2. R minus 4 become 7 over 2. So x power of 4. So this one can be, you simplify it, it becomes something like this. Okay. Then you get the series. Okay, the series is 1 minus 1 over 2x square, 2x plus this one. So here, the moment you already solve the issue of r, then we change your x is negative x over the power of 2. So the x value just now, so we change it to become instead of x, it become negative x squared. So negative x squared square power of 2, negative x squared power of 3, and negative x squared power of 4. Then you can simplify this one. At the end, you will get this type of answer. So this is on the how to use the method. So now we know that integration of sine inverse is become dt over square root 1 over t squared. So by using this series, so we calculate again, then we'll get the answer of sine inverse, something like this. So in the Maclaurin series, there is no sine inverse, but we can change sine inverse into the this method, okay, in terms of inverse integration. Then this one you can use this method. Then you get the answer. Okay. So this is a next examples. You can see it how it works. So use the same one, the series, then they get the answer. Okay. Next we go for L'Hopital rule. L'Hopital rule is needed to find the limits of the form. If you remember, we have learned in your maths ones, or even the early of this topic of ordinary partial differentiation, where is your limit? You have a limit of x approximate to a value of fx function and gx functions, where is fa and ga equal to 0. So means that even though such a limit may be defined, it cannot be found by substitute. When you substitute x equal to some value, you get the 0 divided by 0. So the moment divided by 0, so it's not indeterminate. So you need to use the Taylor's theorems and as specifics on L'Hopital. So where is your L'Hopital is, for example, limit x approximate to a fx divided by gx is equal to, you need to differentiate numerator and differentiate denominator and make sure you won't get 0 over 0. Okay, you keep on doing that differentiation until you get the answer of some answer. Okay, for example, 1 over 2 and the rest. Okay, so it may be you need to differentiate the numerator and denominator in order to find the answer. So here you can see we must repeat the process of differentiation fx, this one, numerator and denominator fgx, each time we have the indeterminate of 0 divided by 0. So when you differentiate above denominator and numerator, when you put the limit, you get 0 over 0. You need to differentiate until it's a non-zero here. Okay, so that limit is exists. Okay, for example here. Okay, for example, using L'Hopital rule to obtain the limit. So limit x approximate to 0 sine x minus x divided by x power of 3. When you put it, your x equal to 0, automatically you get 0 over 0. So this is undetermined. So what you need to do, you need to use the L'Hopital rule, which is your differentiate the above numerator sine x minus x, you get cos x minus 1, and differentiate the denominator, become 3x squared. So when you put it x equal to 0, you still get 0 over 0. So you need to differentiate again above. So differentiate cos x, you will get negative sine x. Differentiate the denominator, you get 6x. When you put it x approximate to 0, you still get 0. You need to differentiate it again until you finish. Now is you get negative cos x divided by 6. So when you put it cos x equal to 0 equal to 1, so at the end of the day, your limit becomes negative 1 over 6. Okay, so means limit of x approximate to 0 sine x minus x power of 3 is equal to 1 over negative 1 over 6. Same like the B. You differentiate above and below, you will get 0. You differentiate second time, also you get 0. So you need to differentiate 3 times here. 1, 2, and 3. Then you will get, when you put it, your limit is 0, you get the answer of 1 over 2. Okay. So as an incorrect answer, since the rule was not applicable, the reader may notice that both of the limit can be readily evaluated by using Maclaurin series. Okay, this is an engineering application. So this is an example of oscillation of pendulum. Okay, the simple pendulum has been used for 100 years. This is the history of pendulums. So pendulum can use a numerical method. So for example, you can see it, you start to understand on how the calculation of the pendulum. This is application of pendulum. Okay, on how to use a Rajkutta method. Here, we use the fourth order Rajkutta method in order to calculate the answer. Okay, so this is the method in order to application. So in terms of the pseudocode, okay, you can calculate it. And this is example of, for example, the first engineering application of oscillation pendulum. So you get the graph and based on the concept of numerical method. Another one is a heating of electrical fuse. So this is also an example of numerical method application of engineering. So you can start to understand on how, okay, based on the notes, how it works and how this method used in engineering perspective. Okay, so I think so we have covered everything here. So thank you very much.